thank you.
Just
so
take it away.
there's lots of rumors, obviously, about quantum, what it can do, what it can't do. And I just was reading an article, or it came by in my LinkedIn feed about quantum AI. So that's even the next step, probably. But this presentation is really about what we can do with some of the interesting aspects of quantum and what is currently actually available. We'll first introduce some of the language. I have to say this is not a physics class, and I'm by far not a physicist, so I only try to understand it a little bit myself. But we'll talk about some of the terminology, some of the abbreviations, which are useful to know if you're interested in the subject and would like to explore further. I've added quite a few links on slides as well, so you can afterwards click on those and find more information there. Then we'll look on how we can use these quantum properties in a mechanism that is called quantum key distribution. And then we'll pull together how to use that QKD system with our current encryption technologies which are available. So let's start with what it's not. QKD is a mechanism that is used to distribute keys. It has nothing to do with generating the keys itself. That's one of the most common mistakes. So it's just distributing keys. The way the key is generated is, for QKD itself, out of scope. There's obviously generators, quantum random number generators, which are using a chip and a quantum processor, but QKD itself is just distribution. Also, you are not transporting any data using quantums or photons or whatever. The way we transport data in this mechanism is just as you're used to, right? So you're still using Ethernet and some encryption, MACsec, for example, IPsec, or any other technology. The only thing we use quantum for is to distribute the keys. So there's no quantum computers involved as well, right? You probably have seen some pictures or maybe things from, for example, the university here in Delft, where they have this whole setup with all the cooling equipment that is needed in order to run a quantum computer. Everything we're talking about here can be used at room temperature, right? So there's solutions already available, commercial solutions, for example, from Toshiba and ID Quantique and many others. And they are just working without all this high cooling. So it might still sound a bit spooky, but it's maybe not as spooky as you think. So let's first start with the problem statement. Why is QKD interesting and what problem does it solve, right? If we assume that at one point a quantum computer does become commercially available, the way quantum computers work, they can really easy, that's the expectation at least, factor prime numbers. And as you might know, the majority of our security mechanisms we currently know are based on prime numbers, right? But the hardest part for a computer as we currently know it is obviously factoring those numbers. So multiplying prime numbers is relatively easy, but now try to factor it back to the original two numbers you used to construct the key. So again, the expectation is that a quantum computer would have much less issues with factoring those numbers. So every current key distribution mechanism or protocol as we know it that is based on those prime numbers will probably be vulnerable to quantum computers. The biggest question obviously is will we at one point see quantum computers that are so powerful? The way they do it is described as Shor's algorithm. It's an algorithm that is written for quantum computers to factor those numbers. Again, we're only touching the surface here because I see you have only 19 minutes left. So let's talk about some of the language that we're using in quantum. In our world, which is referred to by the physicists as classical networking, so we're all classics already, they use qubits, where we use bits, and a bit is either 0 or 1. In quantum, there's a qubit. And the aspect of a qubit is that it could be a 0 or 1 or anything in between. But you only know if it's a 0 or 1 or something in between if you measure it. And some of the really interesting aspects of a qubit, which makes it really interesting for security, is that you cannot copy it. As soon as you would copy the photon, in this case we're talking about photons, the quantum state will be lost. That is also one of the biggest challenges, because if you send a photon over fiber from Alice to Bob, and there is something in between that does regeneration or does something with the optical signal, the quantum state is lost. So that is also a challenge, because with current available solutions, you cannot pass or cross any distance longer than around 120-ish kilometers. Some claim 180, depending on the quality of the fiber. So that is also a challenge. Another thing you might have heard about is superposition. And superposition is comparable to if you combine two audio waves of different frequencies, you would hear the sum of the frequencies. If you compare it to electricity, for example, there's 230 volts, but there's also 380 volts available in your shop or at your house or whatever. The 380 volts you get by phasing one 230 volt signal just a little bit different than the other one, and by adding them together you get 380 volts. That is sort of comparable to how superposition works. Again, the downside of superposition, a photon that is brought into superposition, is that if you transfer it over fiber with optical components in the path, you lose the quantum property, so you lose the superposition. Also, again, you cannot copy it as well. So teleportation, always referred to in some of our favorite movies, is that you could physically transport yourself to a different place. That's not true, unfortunately, and that won't be true anytime soon as well. What you can do is use teleportation to transport quantum states from one side to the other side. And the interesting thing here is that if you bring two photons really close together, then they can take over the properties of the other photon. So in other words, if you, as I mentioned, if you read or observe the photon on one side, it collapses its superposition into the 0 or 1. The same will happen on the other side. And that is the interesting part of what we're using to transport that data. Again, this is just really scratching the surface. So, as I mentioned, some of the advantages of using this quantum technology in qubits is that you cannot copy qubits, right? If you, what I just mentioned, if you would observe the state of one qubit, so let's say you try to interfere in the path and you observe the photon that was being sent to Bob, then the photon at Alice will collapse in the same state as well. So Alice will know that someone has observed the photon. Another advantage is that it's using physics over math. As I just explained, once quantum computers become available, it's expected to be much easier to factor prime numbers. What we just saw and discussed with quantum, you're not using math to distribute those keys to the other side, right? You're using physics, and so it's much harder to crack that, obviously. Some of the challenges, decoherence, for example, it's the current time that one of these photons that has been entangled with another one can keep the same state is still really short. So you cannot really store for a longer time a qubit, and that is one of the biggest challenges as well, for example, currently in quantum computing, that it's really hard to store those photons. That is why they have all these supercoolers, for example, but still you can only store it, I think, currently at maximum of a couple of minutes. So it's only usable still for sort of real-time applications. Also, fidelity is a problem. Fidelity describes or is a number to express the chance that a photon that Alice has and that Bob has, and which are entangled, are different if you observe the state, right? You could sort of compare it to that there's errors in the path. So Alice observes that it's a 1, Bob observes that's a 0, right? And fidelity is good enough currently for some applications, like, for example, QKD. And scaling is an issue, right? If you, as I mentioned, maximum path is around somewhere between 100 and 180 kilometers. That would be interesting inside Amsterdam, for example, but transporting between Amsterdam and Düsseldorf or Paris or whatever could be a challenge. Also scaling in bringing this from point to point to multipoint doesn't work. You can only currently entangle 2 photons, right? It would be really interesting to entangle 3 photons, for example, for multipoint. So another thing that you probably have heard people mention is a quantum internet. So let's look at what is a quantum internet, or is it quantum networking? There is no quantum internet yet. Current quantum networking, as we just discovered, is just point-to-point, right? So it's 2 end nodes, which are able to, one will send a photon and the other has a detector that is able to read out the quantum state. That could be either over telecom fiber or free space using satellites. So there's a couple of commercial parties who are currently building solutions also based on satellites. So it's very comparable to point-to-point networking. As I mentioned, the issue with that is that it doesn't scale yet. So it's really not an internet yet. Current work is going on at, for example, TU Delft and other universities to overcome that that distance limitation by what they call entanglement swapping. As you can see in the middle, there's, for example, A and B. They can entangle 2 of these photons. B and C could do the same, and then you can swap the photons between at B. So A and C have entangled photons between them via a hop in the middle. Also, there's currently not really an OSI model as we know it in classical networking, but they're working on that as well. You might have seen the test TU Delft did with Cisco and KPN recently. Really interesting video on YouTube that sort of shows how this quantum network currently works, but again, it's just point-to-point. And as I mentioned, it's not always perfect quantum state, so the fidelity is somewhere between 0 and 1. For QKD, what we're now discussing, a fidelity of 0.8 is good enough. So the way we currently see these networks working is, if you look at the picture, all the blue nodes are just classical routers as we know it, but they will probably have in the future a separate plane that will take care of the quantum channels. So you will see either quantum information being sent over a different fiber, or in a CWDM, DWDM environment being in a separate channel. There is work going on where they try to send data over the same channel, but lots of that is still, as I think in marketing terms, or still marketing, it is in the end just using another channel on a CWDM or DWDM system. So there is no way yet to send both classical and quantum data over the same link, except by using CWDM or DWDM. So some of the possible applications for quantum could be clock synchronization, right? If you have a classical channel next to the quantum channel, you can distribute when exactly, for example, to make it really simple, you should read out the photon, and if they flip at the same time, then you can use that for synchronization. Obviously, communication between quantum computers, right, to send qubits between quantum computers and so share memory. In this case, we're using it for quantum key distribution. So let's look at how quantum key distribution works, right? We probably all sort of understand how symmetric key cryptography works. Alice and Bob want to share information. They don't want you to be able to intercept with that, so they agree upfront on a key that they will use to encrypt the packets they send in between. The biggest question here is, symmetric key cryptography is quite secure, right? If you are aware that someone is able to intercept your messages or encrypt the key, you just increase the size of the key. The biggest question is, how do you transport the key to the other side? And that is where QKD can help. As I mentioned, why does that work? Because current public key cryptography is all based on mathematical challenges, right? Using prime numbers, for example. So RSA, Diffie-Hellman, and even post-quantum cryptography. QKD, as I mentioned, is relying on physics. So it's much harder to crack that, and as we've seen, you cannot copy this qubit, and if you try to intercept and observe the state of the photon, the other side will know. So a protocol was invented in order to use these quantum aspects to transport a key from Alice to Bob. It's called BB84, named after Bent and Brassard, who invented this protocol in 1984. So just to give you an idea how it works, Alice sends polarized photons from towards Bob, and these photons can be in, as we saw, different superpositions. In other words, she polarizes the photon, so it's either pointing upwards 45 degrees, 135 degrees, or 90 degrees. And she sends those photons over this quantum channel. Then they will do a measurement over those photons using a locally generated filter. And the filter is either a cross or a plus. So the plus will path the photons which are either in upward position or 90 degrees polarization. The cross will pass photons which are in 45 degrees or 135 degrees polarization. Bob will do the same. He generates a local filter and filters the photons. And so if you look at, for example, in the first example on Alice's side, you see the photon is pointing upwards, or the polarization is pointing upwards, the filter is a plus, so the measurement will pass the filter. The second is pointing at 45 degrees, but the filter is either 0 or 90 degrees, so it won't pass and you get an unexpected result. Now, if both Alice and Bob exchange their filters, you see that in some cases they will have used the same filter. In other words, the first measurement will actually create a 1, the second will fail, the third measurement will proceed as well. So now if you sift through the results, you will see that the outcome of the measurement on both sides is 0, 1, 0, 1. And obviously the result is then that the key in this case is 0, 1, 0, 1. Really short again how this works. But by doing this, and for example, if now someone will try to intercept this communication, you obviously, as it's using both a quantum channel and a data channel, if you intercept the quantum channel, then you might see the photons and you can apply your own filters, but you don't know which filters Bob have generated. And Bob and Alice exchange those filters via a public data channel. You would need to intercept both channels, but by, as we mentioned, the properties of a qubit, that it collapses, it would be really hard for an interceptor to regenerate the same qubit and send that to Bob. That is why this is considered to be really hard to crack. Now let's see how we can use that in routers, right? Again, we have Alice and Bob. And Alice and Bob have a encrypted channel in between. As I mentioned, could be MACsec or IPsec or any other protocol to secure or maybe authenticate a routing protocol. And now they will start using this quantum, a QKD system, quantum key distribution system to communicate on the key. So in this case, Alice and Bob, and we have obviously our friend Eve, who tries to intercept in the conversation. So both Alice and Bob have a QKD device. Alice is the sender of the photons, and Bob has a photon detector reading out those quantum states. Both also have a router at their side. And now this is in basic how it works. There's 3 channels in between, a quantum and a data channel between the QKD boxes, and an encrypted data link between the 2 routers. Now Alice requests a key from the QKD device using an interface, which is a REST API that is defined by Etsy. So she sends a key request to the QKD device. Obviously, she gets a key back and a key ID. Now, the only thing the router on Alice's side has to communicate to Bob is the key ID over the data channel. And Bob can use that key ID to request a key from his own QKD device. And obviously, in ideal situation, he gets the same key back, and they can use that to encrypt the communication. So where is this applicable? As I mentioned, most QKD vendors expose a REST API, which is defined by Etsy. So you can just request those keys via this REST API and use it in many symmetric key algorithms and protocols, right? It could be, for example, MACsec or IPsec, or authentication of routing protocols using TCP/AO. The thing is, you need a mechanism that allows for key rollover, obviously, right? And the thing is, or the interesting property is that they can generate these keys at pretty high speed, so you could potentially do a key rollover, for example, every minute. But yeah, then your protocol needs to allow for hitless key rollover, otherwise your communication will be interrupted every minute. So that is what is currently available. I don't think we're there yet. I don't think this is, as it currently is, really interesting because of the limitations. So there's quite some work still to do. I've put a few bullet points up here. So I think the biggest point is obviously the distance limitation, but also that it is only usable point-to-point. Now, what if you have, for example, small point-of-sale offices, remote workers, etc., who would want to use those keys, but you do not want to put around 100k euro photon detector at your house, for example, right? And you don't have a satellite on the roof, etc. So how are you going to distribute those keys, which via non-quantum channel, but quantum safe? So there's a lot of challenges still. If you're interested in the subject, you might have seen a few links on the slides. Here's some further reading as well. There's quite some work going on in IETF. There's quite a lot of work being done by universities, especially a university in Delft. And are there questions? Is this interesting? Is it applicable? Will we ever see quantum computers? Much still unknown. But I think it's a fascinating subject.
Well, the way I see it, there could be no questions, or there could be one question, or there could be anything in between. But the moment we ask how many questions there are... So, any questions?
Well, there is one question from the audience, from online. It's from Bert Hubert, and the question is if you can comment on the NSA paper that says NSA does not consider QKD a practical security solution for protecting national security information.
Sorry, one more time, which paper?
It's an NSA paper that says NSA does not consider QKD a practical security solution for protecting national security information.
It's interesting fact that the NSA is saying that, right? Because as we saw, it's really hard to intercept key distribution using physics. So I can see why some state actors are not really interested in using this or seeing this widely deployed, because it could make their job quite hard.
Yeah, that's not practical.
Any other questions? Robin.
Is that another question from you, Robin? Yeah?
Yes, hello. What are the practical uses that would require quantum key distribution? There's a lot of crypto going on, from banking to Bitcoin. Where would QKD be useful first? And will something like this be necessary for all crypto in the future?
It is practical if you are very, very worried about distributing keys, obviously. So if you, as you mentioned, main interest is, for example, from financials, financial companies, trading companies, high-speed trading as well. If it is, but as I mentioned, I don't think it is practical enough yet that it is really usable, right? You have to imagine this is at a stage where we were with the internet 30, 40 years ago, where you could send a few characters and then it would crash the system. That is where I really see this is now, right? Many of the things, especially in the field of quantum computing, are still research projects, right? So it works under very specific circumstances in a lab in the university. But even, as I mentioned, they can preserve a qubit for maybe a few minutes, right? So that's far from practical. So this is really early stage, but I think the promise is really interesting, especially if we see quantum computers becoming more powerful. Because if we come to a certain point where potentially a quantum computer could crack our current security mechanisms, then you want to know how this works and want to start using this, obviously. But we're not there yet. We're still safe for at least the next 5 to 10 years. So that's the good part.
And for general purpose, like HTTPS, TLS, will something like this be necessary?
Could be, yeah. They are vulnerable to quantum computers. Yeah, definitely.
Okay, thank you.
All right.